Welcome to this third lecture on Lie algebras. So we'll start off from where we left the last time around. We had come, I think we had done lemma 4.4. We had stopped at this lemma 4.4, where we saw how we can construct new solvable ideals from existing solvable ideals. Like if we had a solvable ideal, then every sub algebra was solved. So if L was solvable, then and if you had a sub algebra M, then M was solvable. Again, if you had a homomorphism of Lie algebras and there was the image, say this is phi, there was say phi of L, then that image was also solvable. So we've seen this, and then we've also seen, okay, there was another B part to it which we'll use in today's lecture. That is, if L by I and I, if there is an ideal and suppose the quotient is also solvable, then this would imply if these two are solvable, then L is solvable. And finally we have seen again a result which we'll use today is that if I and J are solvable, then that implies that I plus J is solvable. Okay, so these things we are going to use in today's lecture. So we'll talk about something called a radical. We'll also see the definition of nilpotent and maybe an example. So that is the plan for this particular lecture. So yeah, let me erase and let me start afresh. Okay, so corollary from your books, if somebody is following the textbook, it is corollary 4.5. Okay, so what does this talk about? This talks about something called a radical, which we will see. So let L, okay, let me state it. Let L be a finite dimensional Lie algebra there exists a unique solvable ideal of L which contains every solvable ideal, which contains every solvable ideal of L, and this ideal is called we'll write here RADL. It is pronounced radical L. Okay, so this is for a radical. If I get the spelling right, I hope it is radical, not radical. I'll just check. Just check that spelling of radical. Radical, okay, CAL, it is radical, I'm sorry. So it is not CLE, it is CAL, radical. Let me make that change here. Radical, yeah. Okay, so we'll prove this result. So proof for this, a proof will be fairly simple. In fact, I'll explain to you in a diagram here what's going on. So you have your L, and what we are saying is there's going to be this ideal RADL, radical L, and any other solvable ideal is inside this. So this is kind of the largest solvable ideal that we will have inside L. I mean, radical L could be the whole of L, that is if L is solvable, or it could even be only 0, in which case we will say that we'll actually be calling the ideal semi-simple. We'll see that afterwards. So how do I prove this? The proof is, and by the way, this finite dimensional is very important, otherwise we can't prove this. So this finite dimension will come because we are going to use dimension. So how do we go about the proof? So let R be the largest dimension solvable ideal in L. Now you'll say this need not be unique, of course. If say this L is a 20 dimensional vector or 5 dimensional vector space, we know every subspace has to be up to maximum 5 dimensional. So whatever are the solvable ideals, if this is dimension 5, then those solvable ideals will be dimension 0, 1, 2, 3, 4, 5. Among them, maybe there is no ideal of dimension 5 that is solvable, then you will find one of dimension 4. If maybe there is nothing of dimension 4 also, then dimension 3. So at least dimension 0 will be there, that is the only 0. So yeah, you can just, you know that you can find this because L is finite dimensional. You can find the largest dimensional solvable ideal. I am no way saying this is unique. There could be many such ideals. So but we are going to show that it's going to be unique. So let R be such. Now let I be any other solvable ideal, any other or any solvable ideal of L. So I am taking I. Now if I could from here show that somehow I show that I is contained inside R, that means any solvable ideal you give me, it's inside R, then automatically this result gets proved, because that means R, which had the largest, and every other solvable ideal is contained inside here. That means this is the kind of because from the fact that having taken any other solvable ideal, it's inside R, then R becomes the largest dimensional solvable ideal. Not the dimension is irrelevant, any other solvable ideal is contained inside R. So quite clearly R will have the largest dimension. And not only that, you will see that in that dimension also, if you had taken I of the same dimension, that is still inside R. But if they have the same dimension, one is contained in another, they are the same. So yeah, you realize that the uniqueness part gets automatically taken care of if I can somehow show I is contained inside R, because even if they don't have the even if they have the same dimension, they will become equal, and if this has lesser dimension, it will be properly contained inside R. So all I have to do now is to show that I is contained inside R. So that's what I will do. So let me erase this. How will I show that? Again, it's fairly simple. So you look at this R plus I. Now the dimension, what is the dimension of R plus I? We know that this R plus I, it has to contain what is that? In fact, I will write it the other way around. Let me just okay. I will look at this R plus I, and I will end up concluding that R plus I is the same as R. How will I do it? 1, of course, we already know R, it has to be contained inside R plus I. But why should R plus I be contained inside R? Why this way? That way because R plus I is solvable. And that comes from the previous lemma, which said if I is solvable, J is solvable, that I plus J is solvable. So R is solvable, I is solvable. This implies R plus I is solvable. And also R plus I has to be contained in, oh, not also, this implies actually, yeah, this would imply also, this implies that R plus I is contained inside R, because R is the largest dimension solvable ideal in L. So there is no way that this is not proper. This obviously R is contained inside R plus I, we know that, but now they have to have the same dimension. Since, yeah, I won't write the reason here, but I'm telling it to you. R is the largest dimension, so this cannot be anything more than R. So in fact you can conclude from here that R plus I is actually equal to R. By the way, I hope you all know this, that something I have not mentioned, I have not written, but I'm keep saying this. When you have R plus I, you should know that R is contained inside R plus I. That's very easy, because what is R plus I? Everything that is of the form something in R plus something in I. Well, 0 is there, so you can always have R plus 0, which will give you everything from R. And also I is contained in R plus I. But now we are saying that R plus I is equal to R. So that means I is contained inside R. So this implies I, which we know is contained inside R plus I, will now be, the battery is going down, just a minute. Okay, that will be what is that? This is equal to R. So this implies I is contained inside R, and that proves this particular result. So I'll just connect my battery, because the battery went down. Sorry, not connect my battery, connect my charger. Yeah, okay. So yeah, so that proves this particular result. Let me make a definition now. Yeah. Here's a definition. I've just told you, semi-simple. Non-zero finite dimensional Lie algebra. So a non-zero finite dimensional Lie algebra L is said to be semi-simple if it has no non-trivial, so non-zero, non-trivial, it doesn't matter, non-zero, in fact it matters, because yeah, it does matter, because non-trivial would include 0 and the whole L. Here I am specifying non-zero. If it has no non-zero solvable ideals. Very important, this non-zero is important. That is, so if it has no non-zero solvable ideals, then the largest solvable ideal will be 0. So in this case, radical L would be equal to only 0. Of course, 0 is always solvable. You know what is solvable, right? You construct that, series, yeah, a sequence. You look at this L raised to 0, which is L, and then you have L raised to 1, which is actually uh, L, and then L raised to 2, which is L raised to 1, L raised to 1. You construct this sequence, and if this at some stage for some m, if this L raised to m becomes equal to 0, then you say that L is solvable. Now if you start with 0, then obviously it's solvable, but there is no guarantee any other, apart from 0 you have no guarantee anything else is guaranteed to be solvable. So if in an ideal, if it happens that nothing else apart from 0 is solvable, then that particular ideal, so that particular, if in a Lie algebra L, if nothing apart from 0 is solvable, then we say that Lie algebra is semi-simple. Okay, so let's look at an example. So I'll look at an example. In fact, we have a nice example of a semi-simple Lie algebra. Let us analyze R3 with cross product. So we'll look at R3 with the cross product, and we'll actually show this is semi-simple. Okay, so what do we need to show? What we need to show it is that it has no ideals, apart from 0. None of its ideals are solvable. So we will have what kind of we will have to deal with dimension 3, that is the whole of R3. We'll have to deal with dimension 2, that are those planes in R3, and we'll have to deal with dimension 1 possibilities. Of course, dimension 0 subspace, which would be the ideal, which is only 0, that is solvable. We know that is solvable, so we don't. So there are these 3. We'll analyze all these 3 cases. In fact, we will show that for dimension 2, we will show that there are no sub algebras only. Dimension 3, we have already seen this is not solvable, because that is only one, that the whole of R3 we know is not. So we'll analyze and we'll rule out all these 3, dimension 3, dimension 2, dimension 1. We'll rule out that there, in these 3 cases, that there are solvable ideals of these dimensions. The only option remains is dimension 0, which is only 0, which is we know is solvable. So we have to rule out all these possibilities. So let us do that one by one. So first of all, R3 with cross product has no sub algebras even. Sub algebras of dimension 2. We have seen this before, but I'll reiterate it again here. The reason being why there are no sub algebras of dimension 2 is, if there was a sub algebra of dimension 2, it would be a plane, right? Because it has to be a vector subspace. It has to be plane through, it has to be the plane through the origin. Now if you take 2 vectors in that plane, then we know the cross product of these 2 vectors is perpendicular to these 2 vectors. So the moment it is a plane, you will have 2 elements in that, or 2 vectors in that subspace, whose Lie bracket, this case the cross product, is outside. That means that plane, although it's a vector subspace, it is not a sub algebra of the Lie algebra R3 with cross product. So it has no sub algebras itself of dimension 2. Therefore dimension 2 you can rule out. You cannot, then hence there are no ideals of dimension 2. Therefore no ideals of dimension 2, because every ideal has to be a sub algebra. It's much more, the ideal is much more than a sub algebra. So if there are no sub algebras, how can they be ideal? Then if there are no ideals of dimension 2, how can there be a solvable ideal of dimension 2? So dimension 2 is gone. What about dimension 3? In fact, R3 with cross product itself is an ideal. That's always the case, but it is not solvable. It is not solvable. If you turn back your pages, we have shown that if this is your L, we have shown that L dash, which is now what we say L1, is actually back to L itself, R3 with cross product. And then if that is the case, if you get the whole of R3, then L2, which is, leave bracket L1, but L1 itself is L, so that's again going to be R3 with cross product. So we have seen that this derived series is not is just constant. It remains R3 with cross product for all terms, so it's never going to become 0. So this is not solvable. The 3-dimension one also is, although there is an ideal of dimension 3, it is still not solvable. So that case also is ruled out. And what about dimension 1? Now yes, there are ideals of dimension 1. In fact, every line through the origin is an ideal of dimension 1. So that's easy to see. I think I have explained it before. If you take a line through the origin, then yes, if you take two vectors here, their cross product is 0. So yeah, it is, in fact, these one dimensional ones are what we call the abelian. It is there is only one dimensional. It's abelian Lie algebra. The one dimension, you have one dimensional ideals of R3 with cross product. So every line through the origin is a ideal. In fact, it is abelian because of R3 with cross product of dimension 1. So there is dimension 1 ideal. But are these ideals solvable? So how do you decide whether they are, oh sorry, not ideals, I'm making an error. I'm sorry, I'm making a big error here. Is a sub algebra. Every line through the origin is a sub algebra, not ideal, is a sub algebra. Because sub algebra requires, if you take two elements in that sub algebra and you take their leaf bracket, in this case cross product, it remains. Of course, it remains because you get 0. It's an abelian sub algebra. Is it an ideal? No. Why is it not an ideal? Because if you take, for ideal, you are required to take any vector in that sub algebra, and you need to take a vector outside, and you need to show that their cross product remains within the sub algebra. In this case, definitely it doesn't. You take one vector on a line through the origin, take another vector outside, and look at their cross product. There is no guarantee. In fact, it's going to be perpendicular to both of them. So it's guaranteed to be outside. It's going to be outside the cross product. So what you can state is that, but A cross X, where this belongs to the sub algebra and this belongs to R3. If you take this, there is no guarantee that this belongs to the sub algebra. So therefore, lines through origin, I'll just say there is no one dimensional. Therefore, there does not exist any one-dimensional ideal. So there are sub-algebras of dimension 1, but they are not ideals, and therefore dimension 1 also case is ruled out. So hence the only ideal that will be solvable will be dimension 0, and therefore this is semi-simple. R3 with cross product is semi-simple. Oh, I can't write here because my pick must be there. So semi-simple. Okay, so this is a discussion which also gives you a lot of insight into this R3 with cross product. By the way, this is isomorphic. I had told you, I had given you an exercise. I hope you all have done it. This is isomorphic to SL2R. That is, if you look at 2 cross 2 matrices with real entries whose trace is 0. So trace 0, that is also dimension 3 sub algebra with the L dash equal to the whole of L, both cases. So that's unique. There's no, if you have these two conditions, that L dash is the whole of L and dimension 3, that is unique. So these two are isomorphic. So if you prove something about R3 with cross product, it holds for SL2R as well. Okay, so let me go ahead. In fact, I'll take a new page. So yeah, here is a lemma. Lemma 4.7. If L is a Lie algebra, then L by a radical L is semi-simple, We need to prove this. That take any Lie algebra. So what we are saying is take any Lie algebra L and look at that largest solvable ideal, that is your radical L, and yeah, then you form your cosets and you look at that quotient L by radical L. That quotient will not basically will not have any non-trivial solvable ideals, which makes sense because you've kind of maximized your solvable ideal, and then with that quotienting, you've done this in groups rings very often. When you've maximized your possibilities in a sub object, then when you look at the quotient, that quotient will not have those properties, because yeah, whatever whatever Lie bracket occurs, suppose x plus radical L and y plus radical L, whatever Lie bracket thing is occurring, that's occurring at xy level, which are outside this. So it's kind of expected intuitively, but let's actually prove it. Let's actually prove this is so. So yeah, we will use something called the correspondence between ideals, which we have seen. So let me recall that particular result. We have done this, something called a subtopic correspondence. We did this in class, meaning when we actually had a physical offline class. Correspondence between ideals. I'll just recall what we did. what we did was we said that there is a bijective correspondence. There exists a bijective correspondence between ideals, no, between elements of L by I, where I is an ideal, L by I, and ideals of L which contain I. Okay, and I'll tell you how that correspondence looked even. It's nice to recall it. I'll rub this bit. Maybe I'll keep it. Maybe we'll keep it. So what we had was, if you remember, what we said was, you look at this L by I, you have L, and they are actually, I should have drawn them. They are exactly, what I'm saying is, you look at I here, and then you'll form L by I, right? You'll form the quotients. If you take one of these elements of L by I, there is a ideal here which contains I. There is an ideal here, let's say J, which contains I contained inside J. And what is that correspondence? This fellow gets mapped to this via, what is that correspondence? So how is this bijective map? We look at J by I. J by I is a something, these are what? Yeah, this is a J by I is it's a subset of L by I, because L by I has elements of that form, right? These are elements of, it's I plus some element from L. So you look at this J by I, which is a subset of L by I. Oh, I've just, what I've said, there is a bijective element here, and yeah, this is fine. And so here I take this J, and it has to be mapped there to exactly J by I, which is oh, that is just a minute, just the ideal. So I'll just turn back to that ideal correspondence that we had done. Yeah, correspondence between oh, it is ideals in L by I. That's between elements, no, ideals. Yeah. Oof. Ideals of L by I. So now it makes sense, right? Because so these are elements. Out of these you'll have an ideal, and you'll have this ideal here. So yeah, you will have an ideal here, not an element. It will be an ideal, an entire ideal consisting of certain elements, and that ideal is mapped to j by I. Now j by I is going to be all elements that will be of the form j plus I, where j is in j. So you'll get many of these elements from L by I. It turns out they will form an ideal here. So that was the correspondence, that j by I is equal to the ideal that you start of L by I. J by I was equal to this ideal that you start. That was the correspondence between ideals. So if there is a bijective correspondence between ideals inside L by I and the ideals of L which contain I. You start with an ideal here inside J by I, it has many elements of J by I. There is an ideal J, sorry, L by I, there is an ideal J containing I, and when you look at J by I, that is, you look at everything of that, all those elements inside L by I which are of the form something from J plus I. And of course this will have more than just I, because J, of course if J is equal to I, then this will only, J by I will always give you I. So if J is equal to I, then this ideal only has one element, that is I, which makes sense. If so, yeah, then this J by I has one element and the ideal has one element. So that was the bijective correspondence between ideals. Now we are going to apply this bijective correspondence between ideals to, by taking I to be equal to radical L. We are going to take this as my I and apply this particular result. So let's do that. So let's look at what happens to the situation when I have, so yeah, I have my L and I have this is L by radical L. So I take an ideal inside this. So this is, of course, you can think of your radical L here, and then you've kind of broken up your entire space and you're looking at a particular, so this was your radical L and you're looking at an ideal of radical L. If I start with an ideal of radical L, to show it is semi-simple, I need to show that the only ideal that I will get, solvable ideal here, is going to be trivial. So I start with, I will be calling this J bar. This J bar is going to be a solvable ideal inside L by radical L, and I will end up showing that this J bar is only 0, and therefore I can conclude that L by radical L is semi-simple. So let me do that. So let J bar be a solvable ideal in L by radical L. Then by this particular correspondence between ideals, there exists an ideal J of L, a radical L contained inside J, very important. So you will have automatically, we know we'll have a J here, and that J will contain radical L, such that what is this J bar by this correspondence, such that your J bar is equal to J by radical L, right? That's how we get it. We get this J, and then when you take J by I, you actually get this particular ideal. So J bar is J by radical L. Now J bar is solvable. That's what we have said. We started with a solve. So this is solvable. This is solvable. Not only J bar is solvable, so that means this is solvable. and radical L is the largest solvable ideal. So this is solvable. Now we have done a result. If L by I is solvable and I is solvable, then J is solvable. So by using the previous lemma, we can conclude that this implies that J is solvable, because the quotient is solvable. Radical L is always solvable because it's the largest solvable. So J is solvable. And of course I need to show that J bar is only 0, but that I will do now. So J is solvable. Radical L is contained inside J. That means what? Radical L is the largest solvable ideal. Now we've shown this J is solvable. So this implies J actually is equal to radical L. So that J is actually equal. Radical L was supposed to be inside here. It's equal. Now if this is equal, J is equal to radical L, then what is the quotient where the, say, a group and the in the normal subgroup, or the ring and the ideal, or the, when these two are equal, the quotient is only 0, because there is nothing that can come in the quotient. So this automatically would imply that if J is equal to radical L, J bar is only 0, or in other words, J bar is, you would usually write only what is that, it is J by radical L. This will be only J, because J is equal to radical L. But here anyways, in J by radical L or radical L, you can write it, it's up to you. Radical L is the 0. So anyways, we don't write this way. Now we are used to writing only 0. So this, you'll get J bar is only 0, because this is, it will be only radical L when radical L is the 0 in the quotient. So this implies if J bar is only 0, or only radical L, then this implies that what did I do? I started with let J bar be solvable ideal here, and I showed that solvable ideal is only 0. That means that it's 0, only 0 is the only solvable ideal here. That means L by radical L is semi-simple. Semi-simple. Okay, so that proves this particular result. Now, yeah, let us go ahead. I'll open a new page. In fact, yeah, we could do that in a new lecture. I think it's better we start with a nilpotent in a new lecture, and then we'll take it from there. So I think I'll stop this lecture here.